And thank you everyone for joining. This presentation will be basic statistics in R, as Lauren said, and we'll have some time for questions at the end. Realize that statistics in general and R in general is a lot of content to cover in 1 hour. So this will go relatively quickly, but just know that there's time for questions. That's also why we post the code and the slides for viewing later. So. Overall game plan for the next hour is to briefly talk about downloading everything that we'll need. If you were able to attend the other data management presentation that occurred yesterday, this was covered a little bit. So don't want to be too redundant, but just want to make sure that, especially if this is your first time viewing any of this content, we want to make sure that you have what you need to successfully interact with R. So we'll briefly talk about downloading RStudio. And then we have some data that you'll be able to interact with. Again, all of our materials will be made available to you. And then we'll talk about some specifics about the data we're going to be working with. And ultimately, because we're framing this around statistics, we want to be thinking about what are the types of questions that we want to answer. Ultimately, that's going to drive the analyses that we are going to conduct. And so we'll talk about that, and then we'll actually go into R and we'll do some live coding. So all of the slides, as well as the R code, is available, as well as the CSV files for data. And then at the very end, we will have time for questions. So I believe Lauren will be monitoring the chat if anything comes up in the meantime, but we will go ahead and proceed. So starting with downloading R, again, this was briefly covered in the other data management presentation yesterday. You'll want to go to the R software or R project website. And then when you go to that website, there will be a little link that's kind of not immediately obvious, at least it wasn't to me, that tells you to download your appropriate CRAN mirror. And this was a little bit confusing to me when I first started as well. You'll click on this link and ultimately, and you know what, I'm just going to show you just because I think that might be helpful. So let me share my desktop here. And so when you click on this R project page, you'll get to this R project web page, and then you're looking for this to download R link, in which that will bring you to this web page. You can scroll down, and as I was reviewing my slides, I discovered that the CRAN mirror that I used, which was for University of Kansas, was no longer there. So it doesn't matter which one you pick. You can pick whichever one's closest to you. If you have any particular affinity for any of these universities, that's fine too. It doesn't really matter, just pick one. And then you'll click one, and then you can go through and download either R for what Windows or whatever you're using. So just wanted to show that because I didn't think that it was necessarily straightforward. The other thing, and this is part of the download process, you'll be reminded to download Xquartz if you're a Mac user, and that will be required for interacting with R. And then the next step will be to download RStudio. So RStudio is the interface that a lot of people really like using. A lot of statisticians, including myself, prefer to use RStudio simply because it's a really nice way to kind of holistically interact with all of the information that you might be working with. So you can have your scripts up, but you can also see how your output looks. You can look at your output and your visualizations that you're creating. You can also look at your data, how big it is, how many rows, how many columns, things like that. So we really like RStudio. Once you download RStudio, there's not really a reason for you to open the R software itself. So just keep that in mind. But just know that moving forward, we're going to be exclusively working with RStudio. So you'll see this in a few moments once we get started coding in R, but you'll open RStudio. We'll want to set our directory to downloads. and we can then download the or bring in the data from the data week folder that you all have access to. And from there, you can start working with your data. So before we get into R, again, just want to ground ourselves into a little bit of a conversation about statistics because this is a seminar about statistics and R. So anytime you're doing any sort of statistical analysis, you want to remember and remind yourself of what it is that you're trying to analyze. So you want to be asking yourself, what is my question? What am I analyzing? And what does my data look like? So I really like this schematic that's on the screen now because it encourages you to walk through and think about what does your data look like. Ultimately, your data may look a certain way, or you have a certain question in mind. That's why I really like this schematic. So, while this is not certainly a comprehensive um, a list of all of the approaches that you could use for statistical analysis, it is kind of just a very brief introduction of the basic types of tests that we interact with and covers a lot of important concepts. So again, I really like the way this schematic is set up. So right off the bat, oftentimes your data might either be what we'd call continuous or categorical. So categorical might just be a bunch of different groups that you're trying to see if there's a relationship between those groups of data. And then continuous data actually has numeric values in which they have some sort of distribution that you want to interact with. So here on the left, we have, okay, you have some sort of data set. Here we have birth weight data that we'll be looking at momentarily. And it's continuous, it's measured in grams. And then the question becomes, okay, well, how are you going to analyze this data? And one question that we often think about is how is this data distributed? Is it normally distributed or is it heavily skewed? Is it a distribution that's some like bimodal? A variety of different options, but again, we want to be thinking about what does our data look like because that informs the most appropriate way to analyze the data. So sometimes you'll hear the terms parametric and non-parametric. Really, especially as it relates to this seminar, what's important is that on the left side where we talk about normally distributed under continuous data and parametric, generally what we mean is something that sort of has a bell curve shape. It's something that that's generally what you would expect for normally distributed data. It doesn't have kind of an unusual or a skewed distribution like that. We'll see some examples of that shortly. And then after that, notice here that we talk about different groups. So you could have two groups, you could have more than two groups. For the scope of this seminar, we're not going to be talking about instances in which there are more than two groups, but just know this schematic is here to help you make an informed decision about the appropriate analysis steps. So that's kind of our approach, and we'll go through an example shortly and talk about how to best use this schematic, but I just wanted to show you a little bit more about how this schematic works. And then on the far right side, we have categorical data, and these are things that are counted. And again, you'll see an example of that very shortly, and we'll go through in a little bit more detail through an example of how to interact with this schematic. So just as a reminder, parametric, non-parametric. Parametric just means that you're making some sort of assumption about how the data behaves. Sometimes this is just, it's normally distributed. It looks like a bell curve. Other times it's another distribution. But for our purposes, we really mostly, in this context, are thinking about it as normally distributed or bell curve shaped. So this slide here, this is another schematic, but what I like about this one is that it adds a little bit more information about deciding how to analyze data. The other thing that I like about this schematic is that it starts from the top, where ultimately when you have a data set to analyze or you have a research question, you generally know the number of groups that you have from the very beginning. That's just a study design question, which is why I like that the number of groups is placed here at the top. So you could have two groups, And maybe you're comparing, maybe it's like a weight loss study. And in that case, you might have paired data in which you might have a person's weight at the beginning of a study, and then maybe you have their weight at 6 weeks later. That would be an example of paired data. So it's the same measurement on the same person or same unit. And then there's also unpaired data. So maybe you have two groups and you're comparing a treatment versus a control or something like that. And then once you, again, those are more about the study design itself. But once you have decided about, what that is for your particular analysis, then we get the questions back about parametric and non-parametric. And then the schematic helps you decide which test is most appropriate. And we'll talk about parametric and non-parametric a little bit in more detail once we get into R. But finally, again, what I like about this schematic that the other schematic doesn't offer is that once you get to this stage of, okay, I want to compare two groups, maybe I'm looking at a particular lab value between a treatment and a control, and I think that it's unpaired and it's normally distributed. So I'm going to use the unpaired t-test. But there's one extra step, which is to think about the variance between the two groups. And again, we'll talk about that once we switch over to R. So just something to be aware of. So let's talk about our data sets. We have two data sets which discuss or are about birth weight. One presents birth weight in a continuous format and another in a categorical format. So we have either birth weight measured in grams, and then we also have birth weight as a categorical binary variable. So that would be an example where you had continuous data and then it has been binned into low birth weight, yes or no. Finally, we also have a maternal smoking status variable, yes or no. And from there, we decide or may have already had a hypothesis that we would like to test. So from this data, an obvious hypothesis might be, is there a relationship between infant birth weight and maternal smoking? So a couple different ways we could analyze that. We could analyze it as, does maternal smoking, yes or no, have a relationship with low birth weight, yes or no? That is a categorical type question. You have two categorical variables in which you have counts of these different possibilities. There are four different possibilities in this case. And it's, again, two categorical or grouping variables. So this would be most appropriately analyzed with a chi-squared or Fisher's test. So just to walk through that schematic, again, we know we have categorical data. We know that we have two groups. In this case, it's not paired. These expected counts are something that we'll go over when we actually see the data. But again, this is how you would interact with that schematic for categorical. For the second potential hypothesis, again, we're interested in this relationship between infant birth weight and maternal smoking. So it might be that you still have two groups, which is maternal smoking status, yes or no. That could be your exposure. But then you have a continuous value that you want to measure. So that's a continuous variable and a categorical variable. That would be following our schematic here on the left, in which we have a continuous measurement in grams of birth weight. And then it's up to us to decide whether or not we feel this is normally distributed. So we'll talk about that in a moment. In this case, we do have two groups. As I mentioned before, we have a smoking and not smoking group, and this would be non-paired data. So that leads us down to our t-test approach. But of course, what if it's non-parametric? What if our data is heavily skewed? Another place where this comes up is oftentimes if you have a really small sample size, a non-parametric approach is going to be more appropriate simply because with a small sample size, it can be hard to decide if your data are normally distributed. So again, small sample size, a good rule of thumb that we often like to use if you have a sample size less than 30 total, that can be just a general rule of thumb that's often thrown around for maybe it's a more appropriate for you to use a non-parametric approach. So the non-parametric equivalent with two groups would be the non-paired one here, which is the Wilcoxon rank sum test. And we'll talk about those as well. Finally, before we fully switch over into R, I just want to present two more data sets for your consideration. So here we have a cars data set and we have a class data set. We've got both continuous and categorical data in this case. But in this particular instance, we're going to be focusing on the analysis of continuous data. So we have an example of highway miles per gallon versus city miles per gallon. And then we also have a class, simulated data set that has height in inches and weight in pounds. So thinking about potential hypotheses to test for our cars data set, one could be, is there a significant difference between highway and city miles per gallon? Now, this would be an instance of paired data because we would, and if you, again, I think this will make a little bit more sense when we look at the data set, but we have a value for each individual car, one value for highway miles per gallon and one value for city miles per gallon. So that would be an example of a paired test. So again, if we go back to our schematic, we have continuous data here, that's miles per gallon. And then we'll have to determine which side of this schematic we think is most appropriate based on the distribution of the data. We do have two groups. In this instance, it would be the groups are the different types of miles per gallon. And then this would be paired. So here the schematic effectively tells us that we should either be doing a paired t-test if we ultimately decide that normally distributed is reasonable for this data set, or on the right side of this schematic under continuous data, we'll go down under skewed two groups and paired, which will give us the Wilcoxon signed rank test. So one thing to note is Wilcoxon signed rank and rank sum kind of sound similar, but they are in fact different. And the difference is whether or not your data are paired or measured on the same individual, or in this case, unit, which is cars. The last hypothesis that we'll test is maybe we want to know if there's a significant relationship between height and weight of these particular school children. So again, this is just a fake data set that we are going to look at. And in this particular case, we're interested in the relationship between two continuous variables. So this is a little bit different than some of the other tests we've talked about. And this is not in the schematic. So again, the schematic that I've shown you is ultimately not going to encompass all of statistics, of course, but I think it is a really nice first kind of pass at a lot of the types of tests that you might see on a day-to-day basis. From what we have seen, you have some sort of grouping variable. So we had like smoking status, yes or no, and then you had another categorical variable, and you want to know the relationship between low birth weight and maternal smoking status. Or for the second test, you have maternal smoking status as a grouping variable, but then you have birth weight as a continuous variable, and we talked about how to analyze that. But for this fourth test, this is an instance in which you have two continuous variables. So you don't have a group, you don't have an exposure necessarily in which you have values that are binned into one, two, or three groups. This is just simply looking at the relationship between weight and height, and we're not putting any type of grouping into that relationship. We just want to look at how those interact with each other. So let's go ahead and switch over to R. And all right, just checking the chat. All right, great. So again, once you download R Studio, there's not much of a reason for you to click on the R application itself. You can just use the R Studio one, and in order to import the data, you can pull it in by typing in, I know my data is in the downloads folder, or maybe you downloaded the R for basic statistics folder, and that is its own folder within your downloads folder. You can try to code that up. I still prefer just to do a point and click approach. So all you effectively have to do is once you've opened RStudio, you'll click import dataset and then click from text. This data is CSV files. So that is what that from text sort of means. You can also download a package that is more for Excel. But in this particular case, all we have is just a standard CSV file. And just a couple things that I want to point out. I like this point and click option. I think it's much easier than having to actually type in the or program where your data is and what it's called. Here you just point and click, you decide what you're going to name your data set. Here we decided to call it B weight. And oftentimes R is pretty good at guessing what your data looks like. So in this particular case, it knows that we have columns and it knows that we have column names. Sometimes what you'll find is that it may not understand that you do have columns names and maybe you don't. So that's something you can always go in and add later. But sometimes if you look down here at the bottom under data frame, you'll see something like V1, V2, V3. That's an instance in which R doesn't know that this data has column names. But again, automatically it detected that. So we'll go ahead and click import, and then we get our data in this way. So always good to start, just kind of look at your data once you get it in, and you can look at the different variables just so you can understand. The specifics of this data dictionary were discussed on the data management presentation, so I won't go into this too much, but that information is on the slide for that other presentation, but I will, of course, talk about the variables that are related to our analysis of interest. So the matter of bringing in the other data sets, it's the same basic approach. All I did here down at the bottom of my RStudio window, so just to point out here, at the bottom left, we have our console. This is where our output comes out. On the top left, we have our actual script. This is what will open up when you open your R script that we've provided for you. On the far right is a little bit of information about your different data sets. And then on the bottom right is where things like your plots will show up, which we'll see in a moment. So all of that to say, once you decide to bring in your data, I suggest you do the point and click approach from import data set. But you can always copy that output from the bottom and then copy it into your script. And that way you don't have to worry. R is really sensitive to things like capitalization. So it's just easier to copy it down from the output down here, I have found. So same approach. I've brought in all of the other data sets that we'll look at. We have just because I know this can be a little bit confusing, we have a data set called B weight. That is the birth weight data set that we will be using to examine actual values of weight versus smoking status. We have our mom smoke variable here. There's also a birth WGT data set in which we have the smoking status variable, and then we also have low birth weight as a separate variable. So realize that two birth weight data sets can be a little bit confusing, so just be aware that they each house different types of data. So if you remember from the slides, we had four big hypotheses that we wanted to test during this seminar. So the first one is we were looking at what is the relationship between the birth weight of infants and maternal smoking. So in our scripts, you'll generally, after you load your data, or some people prefer to do this before, you'll want to import any packages that you might need. And in this particular case, we'll talk about this in a moment. Tidyverse is a really great package that can be used for data manipulation and summarizing data. I use it a lot. I think it's a really intuitive way to interact with R. So we'll talk a little bit about Tidyverse. But if you haven't already used R or you haven't used this particular package, the way that you would download this package is you would go up to the top and you would click on Tools and then Install Packages. And then you would type in this case, Tidyverse. So type in Tidyverse. You would select Tidyverse. It will autofill in most cases. And then you click Install. For our purposes, we've already have it installed, but I just wanted to make sure you knew how to install that. So we'll first start with this B weight data set, which is the one that offers a continuous measurement of infant weight in grams. And this data set here on the right, we can see that it has 50,000 rows. That's a really, really big sample size. And then it has 12 columns. And right off the bat, you might just be interested in, okay, I know that I want to see if there's a difference in birth weight between these two groups. So maybe you want to know just some summary statistics on that data. I want to walk you through an example of how we think about the tidyverse package and how it can be used, I think, to very nicely step through different ways of interacting with data in R. So what we'll do is we'll start with our data set. It's called B-weight. So we'll just have that typed out. And then we're going to use a concept called piping with tidyverse. So here, piping is just this percent followed by the greater than sign followed by another percent. And then all this is doing is saying, I want to take this data and then I want to do something to it. I want to manipulate it somehow. So what we're saying is we'd like to take our B-weight data set, which has 50,000 rows, and then we want to group by the mom smoke variable, which is this one here, and it's just 0 or 1. And I've noted here that 1 means mothers who are smokers and 0 means mothers who are not smokers. And so what we're telling R is I want to take that data set and then I want you to group by maternal smoking because that's a variable that we're interested in. And then I want to do another of this piping mechanism. And then again, I think I have found, and I know that this is a new vernacular to learn, but I do think that a lot of the dplyr functions that you'll see have a pretty intuitive name. So what we'd like to do is we'd like to summarize. So we'd like to take our data and do some sort of manipulation to it. So if you want to know some sort of summary statistic, a good place to start might be, I'd like to know the mean of the weight value, and I'd like to know the standard deviation of the weight value. So within our summarize function, we will get the mean of weight and the standard deviation of weight, but we're going to group it by smoking status. And once we do that, if you look down here at the bottom, we have our mom smoke variable, either no smoking or yes for smoking. And then we have a mean of infant birth weight of 3,400 in grams for the non-smoking and 3,100 for the mothers who are smokers. And then we have a standard deviation here. So this is just a great place to start when you're trying to get an understanding of what your data looks like and potentially how it behaves. Just trying to get a sense of ultimately informing how to analyze your data. So we have just an overall summary. Another package that I'll show you, again, this is something that you can load if you don't already have it using the install functions under the tools tab above, is the table 1 package. This table 1 package I really like for a few reasons. So let me make this a little bit bigger. And the way this works is we'll use the table 1 function within the table 1 package. We'll use this tilde to say, I want to look at a few different variables. These variables come in the form of these columns in our data set here from the B weight data set. Maybe we're interested in weight gain, education level, and then the sex of the infant. So those are 3 variables we could summarize, and then we have a vertical line to distinguish the variables that we want to summarize and the variables that we want to group by. So here, grouping, just as we've done before, is mom smoke, the maternal smoking variable, and then comma to differentiate and include information about the data set that we are pulling from. So once we do that, we have here a nice little table. One thing that I really like about the table 1 function is that you can highlight this completely and then copy it and then paste it straight into Excel or a Word document. So if you're generating a report or someone has a question for you, you can just put it in an email. It's just a really slick way of interacting with the data I found. And we had a great question here. So this tilde that we have here in line 23, effectively that's just telling R which are the variables that you are interested in having going along row wise to the right of this table. So what you're doing is I'm not really sure why there's nothing on the left side of the tilde, but effectively, you're just telling the table that these are the variables up until this vertical line that I want to do some summarizing for. And that's what you'll find is that those are the three variables to the right of the tilde that are in these rows here. And then we now have them summarized based on, again, 0 and 1, which is either mothers who are not smokers or who are smokers. And the other thing that I'll point out here is that R is pretty good at determining whether or not something is continuous or categorical or not. So what you'll find is that most of the time here, all of these numbers are right justified because R thinks that we should be treating these as continuous variables. But if we go back to the data dictionary, which you'll find on the PDF or the PowerPoint for the data management slides, there are some variables, just like our outcome here, which is, or just like our exposure, excuse me, of maternal smoking. We have these different levels that actually mean something. So education level or the sex of the infant, 0 or 1, those have actual words that need to be assigned to them. So that's why you'll find that I've used this factor function. Factor just tells R that don't treat this as continuous. Don't treat this as a set of numbers that need to be summarized by means. Rather, we want to know, what are the relative percentages of these, and ultimately that is how you would interact with that information. Something else that you can do, which we don't really have time for, unfortunately, in this limited seminar, but you could go through and rename all of these factors based on the data dictionary, and yeah, you can get the information from there. So I'm just saying just a couple quick questions here. Yeah, so factor is effectively just categorical information. We had a question about what does factor mean? That's an instance in which you want that variable to be treated as a grouping variable. And then we had one other question about downloading R and import data sets. So someone's asking, can you repeat how to get the basic stats with R tab? So that's a question that I think Lauren can answer while we proceed, but all of this information will be including the data sets, will be available to download to you. So we'll make sure that we get that information to you by the end of the seminar. So thank you all for the great questions. I usually try to build in a little bit of time to check in just because I know it's a lot of information at one time. So bringing us back into the conversation about birth weight, we've summarized our data. We had some continuous variables like weight gain, and then we had some more categorical or grouping variables where we've used the factor function to basically say like, okay, what is the proportion of males versus females for these newborn infants? And then the next question might be, okay, well, let's look at our other data set. So again, just as a reminder, we did have 2 birth weight data sets. This other one is a little bit larger. It's about 100,000 individuals in the data set. And this is, in some ways, it's nice because our grouping variable, again, similar sort of approach. So we use our table 1 function, we use our tilde, and then we identify the variable that we'd like to have along our rows here. And then we use our vertical line, and then we use their smoking, which is the name of our grouping variable that is ultimately the exposure that we're interested in comparing. When you do that, or when you run that line, and one other thing that I'll point out here, which I don't think I've done yet, is I'm just highlighting a line and selecting on my Mac Command and then return. You can also highlight whatever you want to run and then just select the run function here at the top. So just a couple different ways for you to actually get your program to run or that particular line of code to run. So based on this table here, we definitely have some missing data. You can see that we have some people who are mothers who were not smokers, and we have some individuals who are mothers who were smokers. But we have like 5,000 people who we don't have that information for. for our purposes, and we could absolutely have a totally separate class about missing data. Ultimately, for the purpose of this, I think, especially with the sample size of 100,000, it would be reasonable to just remove those for this case. So in R, there are a variety of different ways that you can remove data and interact with data. I'm just showing you one example. So here we're going back to our tidyverse vernacular. We have birth weight, which is the name of the data set that is looking at birth weight, which is categorized into low, or I should say no or no, low birth weight, yes or no. And here what I'm doing is I'm using the arrow to basically say, I want to create a new data set that takes this birth weight data set and then does this piping where we take that data set and then we decide that we're going to remove anyone with smoking equals an empty factor. And when you look at the data set, when you sort on this, you'll find that sometimes this is listed as NA, and other times this is just reads in as an empty character. So that's something that you'll want to check once you look at your data. In this particular case, what we're telling R is we're going to use, again, this is tidyverse vernacular. We're saying we want to filter only to look at certain rows of our data set. And in this case, smoking is our variable that we've grouped here at the top, and we want to remove those ones that are not, that don't have information that we need. So when you see this for R, the way to read this is smoking is not equal to empty characters. What we're saying is, I want you to take this data set and I want you to remove any of the rows in which smoking is equal to missing. And the way to sort of verbatim read this would be, I want you to only keep the rows that are not equal to this empty character. And that's what this line of code means here. So once we do that, another option for examining something we call cross-tabulation. And this is relevant for the slide that I showed you earlier for the schematic about how do you analyze categorical data. We were looking for something like what was the total number of expected counts in the cell. So again, if you go back to that schematic, then you can look at, okay, a general rule of thumb is if you see any number that's less than 5 in any of these cells that you see down here in the bottom left, that is where you would use a Fisher's exact test. And if we have time, we can go back and talk about how that looks in the schematic. In this particular case, we have a massive sample size, so I think a chi-squared test is totally fair. And I am seeing a few questions come through. I think we'll save those for the end, just in the interest of time. And then here we have our, actually we're conducting the test. So we've gone through, we've identified that we have categorical data, and we're going to run our chi-square test. So again, I think a lot of this, the R packages, functions are somewhat intuitive in their naming, but of course, it does take time to get used to what they're called. Here, in order to conduct a chi-square test, it is this SQ period test. And what we're telling R in this case is we want to take our data set, which is our categorical birth weight data set, and we have our grouping variable for low birth weight, yes or no, and we have our grouping variable for smoking and non-smoking mothers who are smokers. So I'm going to run this function, and we'll talk about the results. Here in the bottom, we get a highly, highly significant p-value. This is 9.46 times 10 to the negative 10. It's a very, 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 very small number, meaning that there's definitely a significant association between mothers who are smokers and low birth weight. Another way to say this would be there's an association between low birth weight and smoking, or we can say that they're significantly associated. One thing that the chi-square test does not do is it doesn't tell you specifically which group is higher or lower as far as percentages between groups. And that's what's great about this table 1 function here to the right, is that you can look and say, okay, so among those mothers who were smokers, 9.2% had infants who were born with low birth weight, and then among mothers who were not smokers, 7.9% had infants who were born with low birth weight. So what appears to be somewhat of a different percentage, this really highly significant value, p-value, is probably largely a function of the fact that we just have a huge sample size here. The other point that I'll make is that there's this correct function. Basically, what this does is R will automatically do a correction in the event that maybe you have kind of a small sample size, just to protect you from making potentially a false conclusion. In this particular case, it doesn't make a huge difference, but that is something that I think it's important to be aware of. And then now we're going to look at our continuous data. So just as we had our two groups before, let's think about our other hypothesis, which is looking at the effect of maternal smoking, but on the actual value measured in grams of birth weight. So a great place to do our first visualization here is the box plot function. And in what we're telling R in this case is we want to take our B weight, that's the other data set. And then what we do is we use the $ to tell R that we want to look at a specific column. So here we want to look at a specific column called weight. And in this case, we're looking at the tilde, and we're telling R that this is our grouping variable. So we start with our continuous variable that we want to look at for our visualization, and then we have our tilde, which is the grouping variable for whether or not you are or the mother was a smoker or not. So looking at the right here, if you'll remember, 0 was the group of mothers who were non-smokers, and then 1 was for mothers who are smokers. It does appear like there is somewhat of a difference here. The birth weight tends to be a little bit higher on the left group. That, of course, squares with our summary measurements that we did earlier. And again, that's just a nice way to visualize your data. We like box and whisker plots or box plots because I think they do a nice job of representing where your data falls. Here, the solid black line represents your median value. And then the box is the perimeter of the box represents basically the middle 50% of your data. And so that's kind of like your 25% to your 75% quartile. Anything outside of that are kind of your external values, and also noting that it appears like there are maybe some outliers in this data set, but this is a very, very large data set. So thinking back to our schematic, we need to think about, okay, how is this data distributed? Ultimately, we have to decide between a parametric or non-parametric test. So one thing that I really like is this QQ norm plot. So I'm going to run these functions and then I'll tell you what they do. If it made this really nice QQ plot, and basically what we're using this plot to decide is how normally distributed is this data. Ultimately, what you want is your data to fall right along this blue line. And in this case, we can see there's definitely a little bit of a skew here, and we'll see that maybe a little bit more easily when we look at our histograms in a moment. But again, what we're trying to do is decide what's the most appropriate test for our analysis. So just briefly to explain what we're doing here, we have the name of the function is QQ norm. We take our data set, B weight, we use our piping, and then we have our filter. What we're saying here is I only want to look at those where mom smoke equals 1, so the mothers who are smokers. And then we use this function called pull, which just basically selects that data set or those numeric values among those who are smokers. And this is the weight value for infant birth weight in grams. And then these PCH and frame, these are just arguments that are used for creating the figure. They're not really worth details worth putting too much weight into. And then I'll make another QQ plot here. This is for our different data set, or excuse me, this is for the mothers who are not smokers. And you can see that they're a little bit different, but ultimately there is this skewing or sort of deviation from this line at the bottom. And I think a great way to look at this, another visualization, is called the histogram. So we can use the hist function and use again, we have our data set. We use our $ to identify the variable that we're interested in looking at. And here, this is telling R, we'd like to look at a histogram of the birth weight data. And you can see that this really looks pretty normally distributed, but there is this skewing to the left, sometimes what we call a negative skew, where there happens to be values that are kind of on the lower end, and maybe that sort of clinically makes sense. That values on the lower end are certainly a possibility. This is also a great time to check for outliers. You want to make sure you don't have values that are like negative 10,000 or something like that. So this kind of trailing off to the left here is effectively what we're seeing in this QQ plot here. So why does that matter? So if going back to the schematic in the PDF file, we need to know whether or not this is parametric. We need to decide if this is normally distributed or not. Since we have such a large sample size, often people will say, this is a big sample size. We use something called the central limit theorem in statistics to say, in most cases, I have a large sample size. I think I can just proceed with using a normally distributed approach or t-test approach. However, because there's a skewing here, some statisticians may say it might be more appropriate to assume a non-parametric approach. I think that both arguments are justifiable. But since the QQ plot looks a little different in that it's not right along the line, let's run our Wilcoxon test. So again, we saw the Wilcoxon test in our schematic. Here, in order to test that, we're using a lot of the same approach that we've seen earlier. So if you remember, we had our box plot and we were saying we want to look at weight given our tilde, given smoking. It's the same kind of approach here. So we have the name of the function is Wilcox test, and we have B weight. Our data set is B weight. The variable, which is assigned by the $ is called weight. So that's our outcome variable given our grouping variable or our exposure variable. And we run that analysis and we get a highly significant p-value, which again is perhaps not too surprising given the summary statistics we saw. And it looks like there's a pretty stark difference here, especially because we have such a large sample size. Even minor differences are going to end up being highly significant in this case. But maybe you have a lot of faith in the t-test. I do, and traditionally tend to default towards the t-test, especially in a large sample size framework. If you remember that second schematic where we talked about the additional step we have to make once we've decided that we're going to go with a parametric test, let's say we've assumed normality. You also have to see whether or not the variances between the groups are different. So we can do a test for that. It's called var.test. And just as before, we use the same approach where we have our outcome variable on the left, we have our tilde, and then we have our grouping variable from there. In this particular case, we get another highly significant p-value that suggests that the variances are different between our two groups. If you look to the right here of our box plot, maybe that's not too surprising because the range on the left group or the non-smoking group maybe is a little bit higher. So maybe that's not unreasonable. So we could run our t-test, and what you would find is that you would get, you have the another highly significant result here. And the nice thing about the t-test is it spits out those means for you, which are, of course, similar to what we saw at the beginning of the lecture when we summarized the data. The other final point that I'll make is that R by default assumes that your variances are unequal. So you'll notice here that if I don't use this var equal argument, I get the same result and it runs the same test, which is called the Welch two-sample test. There are other software like GraphPad Prism that actually don't make the same assumption. GraphPad is going to assume that your variances are equal, and they're going to run just a standard students test or a two-sample t-test. So just something to be aware of as it relates to differences between different software. So I'm looking at the clock now. We've got a little bit short on time, but again, we do have some time for questions, and I'm happy to stick around a little bit longer if that's needed. But let's move on to our next two hypotheses. So the next one was looking at the relationship between city miles per gallon and highway miles per gallon. And if you remember, we decided that this was a paired analysis because if we look at this data set of 428 cars, each row represents an individual car, and we have a value for city miles per gallon and a value for highway miles per gallon. And so maybe our hypothesis is, is what is the average difference between highway mile per gallon and city miles per gallon? We probably have an intuition about which one is higher. But let's look. So we can, again, use our hist function. And once again, we use cars. Cars is the name of our data set. We use the $sign to call the variable that we want, and we're going to subtract one from the other. Here we get our histogram. And what we're finding is that the vast majority of our data falls to the right of 0. So what that means is that the highway value tends to be higher. Otherwise, you would end up with a bunch of negative values. And again, that sort of fits the paradigm that we know and we think about in most cases for gas-powered vehicles. So we have our histogram. And again, the question is there a significant difference between city miles per gallon and highway miles per gallon? We can once again use our QQ norm plot. Just as a reminder, we're using this plot. Ideally, our data falls along this QQ line. That's what this second line in these functions mean. And here in this case, we're just subtracting one value from the other. And we're putting our data from the QQ norm function and measuring that up against what a theoretically normally distributed line might look like. And what you can see is maybe there's still a little bit more skewing. We have this tapering down here at the bottom. And so maybe that's sufficient for you as an analyst to say, that's not good enough for me. And maybe you feel like the Wilcoxon test is appropriate. So it's going to be the same basic approach, but here in this particular case, if you remember, we are looking at basically two variables, and we want to look at the difference between them. So here we have our highway value, and here we have our city value. So this is going to look a little bit different compared to what we saw above, where we had our continuous value, and then we were saying, is there a difference between those two groups? Here, effectively, what we're doing is we're taking two values, and we're just calculating the difference between them. That's what the paired test is doing. So that's why here we use commas instead of the tilde. And then we have the paired argument set to true. That's going to tell R that we are conducting a paired Wilcoxon test. And then here we look down at the bottom and find that we have a highly significant value suggesting that effectively this value is non-zero. So there definitely is a difference between highway and city miles per gallon. I'll just point out, similar to what we saw above, that if you were to do the t-test, you could run these tests and same kind of approach. So you would just select the variables of interest. You would tell R that they're paired, and then you can conduct your test. One other point to make is that you can actually just calculate this difference, because that's what R is doing for you, is just saying for each individual row of data, for each individual car, what is the difference between highway miles per gallon and city miles per gallon? If you were just to pre-calculate this and run a t-test, R is just going to do a one sample t-test, and this is just sort of an aside about statistics, but you would get the same results. So if you look down here at the bottom, and I'll make my console window a little bit bigger, whether you run the paired test, which calculates the difference for you, or you calculate the one sample test, which we've calculated the difference in advance, you get the same exact results. You get the same t-statistic, same degrees of freedom, and same p-value. So just something to be aware of. You can also run it using a linear model, but that's something that is probably not something we need to spend too much time on. And now we are at the end of the lecture. So a few more minutes here. Let's look at our last hypothesis. So if you remember, we were looking at the relationship between weight and height. So another really great way to visualize your data is just to use the function called plot. And here we have, it's just called plot. Just as before, the name of our data set is class. So it looks something like this. We have our two continuous measurements for height and weight. And here we have class as the name of the data set, $ to look at the value. And then we use our tilde to look at the other variables. So in this case, the way that R interacts with this is weight is going to be your y-axis, the way that you can sometimes read the tilde, which is why the table 1 tilde is a little bit confusing. And I understand why there were questions about that. One way to kind of read this is saying, what is the weight given height? And that's kind of how we think about these axes here. So your y-axis is weight, and your height is your x-axis. And here in the plot, definitely somewhat of a positive relationship. As height increases, weight also seems to increase. That sort of makes sense. We can do some histograms here to see what the relative distribution of our data. Does it look perfectly normally distributed? No. It's kind of a small data set as well. But is any data going to be perfectly normally distributed? Probably not. In this case, it seems reasonably okay. We don't see a large amount of skewing here, so I think it would probably be okay. Again, other statisticians might disagree with me. But our last statistical analysis was to fit a simple linear regression. So just as we've talked about before, we're going to fit a linear model. The name of this function is LM. We have class weight is the name of the variable. So we want to look at weight given height, and we'll run that function. And then we get our summary here. I'm seeing that we're right at 6 o'clock. So if you have to sign off, thank you very much for attending. Just got a couple more lines of code here, and then we'll open it up for questions in a couple minutes. Basically, the way that you would interpret these results is that we've assigned our analysis to what we decided to call it LM1. You could call it whatever you wanted. I'm calling this linear model 1. We run our summary function on this object. And at the bottom here in our console, we get our results. So what is this saying? The way to interpret this would be to say, for every 1-inch increase in height, there is about 4-pound increase in weight. So again, that sort of makes sense. As height increases, weight increases among these school children. Logically, that sort of makes sense to me. If you're concerned about the distribution of the data, which we often are, you can use this plot function to look at the actual residuals from your model. So effectively, all we're trying to do is just to say, the residual is the difference between the actual data and what the model thinks your data should look like. And we want this to be normally distributed. That doesn't look super normally distributed to me. Again, we have kind of a small sample size. So maybe it would be better in this particular case. Again, you're looking at the relationship between two continuous variables. So one option could be to look at a correlation. And the way to do that would be to use the core.test function. Here in this particular case, just as we saw before, we have a highly significant relationship between weight and height. Here we also have a highly significant p-value, suggesting that there is a high relationship. Here we're looking at correlations, correlation between these two variables. And then if you really are concerned about the distribution of the data, as I alluded to earlier, if it's a sample size that's really small, it might feel more appropriate to use a non-parametric approach. This was not in the schematic, but the non-parametric equivalent of a correlation or a Pearson correlation is called the Spearman correlation. So the way that you would do that is we have our core test, similar to the way that we thought about our paired test, where we have commas here. And then we use our method, which is the argument we would use for Spearman. And we get our p-value, which again is highly significant. So definitely a pretty strong relationship between height and weight. And that will bring us to the end of the script. So I'm going to pull up these slides here and just see what other questions we have that I might have missed. And I thank you all for your patience. I apologize for going slightly over. Let's just make sure we haven't missed anything here. So Okay, so we had a question about the smoking data set, and we were looking at sort of the difference between NAs and so the question was, is NA included in the data set, or do you set up a function to include the three categories? So by default, this data set is going to read in when you interact with this data set yourself. This data set is going to just have everybody's going to be in it. So let me re-upload it. And here, it's some data sets will explicitly say NA, but in this particular case, for whatever reason, it's filled in as an empty character. And so this by default is going to look that way. And then I have told the function to say, take that data set and we're going to use the filter function. And it's saying basically anyone who is not equal to that empty character. And that's what I'm telling the function to do. And then we had a comment. So yeah, so we replaced the original table after piping, and that's exactly correct. So someone was clarifying what I've done is I've actually overwritten that original table, and that particular table now has fewer rows. We went from 100,000 rows to 94,000 rows, and then I can rerun and do another summary table that way. But yeah, you could, of course, call it something like birth weight 2 or birth weight, like complete or something like that. It's always good to differentiate and know the different names of your data set or your justification for removing things. Here in our particular case, it's easy enough to just reload the data. We had another question. If you eliminate the missing smoking data, does the function also remove the entire row? That is absolutely correct. So the way to think about what does the filter do, filter is a row-wise, generally going to be a row-wise. So that's why we have our observations, number of observations going down from 100,000 to 94,000. In this particular case, it's going to remove everyone from that row. There are ways that you could, if you wanted to keep that information, you wouldn't have to filter them out completely. You could set it to NA. So there are definitely some options there. Let's see here. And then we had a question about sample size. So for a small sample size, is there an alternative way to remove just those missing observations and keep the other variables? Yeah, so definitely a few options. One point to make, so this is a good question. So let's go back to our data set here with birth weight. So I'm going to reload that. Yeah, and we could really fill a whole class about missing data as well, but it's a really great question. So the question is, maybe the other rows of data have value. Maybe you don't want to just remove everything, which is what the filter function is doing. Right? I mean, you have age group, you have race. Maybe you want to summarize on that first. So there are a few options. And for example, in this particular case, if my analysis was, I still want to look at the relationship between birth weight. Here, what I could do is go down to my data set. And probably what I would do is something like this, where I'm saying birth weight, and it's the smoking variable. So what I'm going to do is I'm going to convert these to NA. That way I can keep the number of rows without removing them entirely. So birth weight, $ smoking, we're going to use an if else function. So this is just like a logical function. What I'm saying is in the event that birth weight smoking equals this, so you need the double equals in this particular case to tell R that this is what I want to do. I'm going to set this to NA, and you'll notice this is in blue. That is telling R like this means something. This is a missing cell. And then if it's not that case, if it's not an empty character, we're going to keep that variable the same. And here we'll call it smoking. So now if I look at this data set, instead of excluding all of those individuals, we can now scroll all the way to the bottom and find that we now have a bunch of NAs. So so now you have retained all of the additional variables without having to delete those rows. So if you wanted to go back into your table one and let's say you were interested in some of these other variables that you might have deleted, like let's add race into this. So now instead of deleting altogether, what you'll find is that you still have your N overall is 100,000. It's important to note that because you set these to NA, there will now be this kind of like your no and yes numbers won't add up to 100,000. So that's just something that you could put as like a caveat in a table. But these numbers won't add up to each other because you have those missing rows. But because that information does exist elsewhere, you now haven't removed those rows. So I hope that answers your question. Okay, great. Okay, so last question. Can you also use the same function for missing continuous variables? Yeah, yep. So, and I don't know if there were any particular examples here, but the same argument applies. So you can use this same, and I'll put it in the chat if you want to copy it into your script. But oh, looks like I didn't send it to everybody. So yeah, so in the event that you wanted to do this to a continuous, the other thing that I'll note too is like sometimes I have data sets where it's not obvious to me like what the different characters are. So it's like sometimes it'll be like 3 spaces and not 1, which is sometimes annoying. So like if I reload this data set, a good way to see like the number of rows that, or I guess like if there are extra spaces is to use this unique function. And then here you can see that there's only like 1 space instead of 2 spaces or something like that. But yeah, if this were a categorical variable, you could absolutely do the same thing. All right, let's see. All right, looks like we are at the end. Still happy to hang around if you have any other questions. But if not, I think that we'll wrap it up. So I'll hand it over back to Lauren.
Yes, so thank you everybody for joining us. I posted in the chat the link to our survey to provide feedback on tonight's session and how we will rework and revamp things for next year's Seed Data Week. And by completing the survey tonight, you will be entered into our raffle for 1 of 5 prizes. If you are attending other talks the rest of the week, each additional survey you complete is another entry into the raffle. And then don't forget that on Thursday from 3 to 4:30 p.m., we were going to have our stat soiree. So a dessert hour from 3 to 4:30 at the Fulganiti Pavilion. And we hope to see you there, talk about some of the things that you learned this week, or ask more questions about statistics and coding. Have a great evening.
Thank you. It looks like we got one more question, but if you're ready to sign off, please do so. Someone was asking about generating the vertical slash on a Mac. That is on the far right under the delete. So it would be shift and then it's backslash. Lauren, do you have a Mac or do you have a PC?
No, so I have a PC, and for me, it's also the same slash key. It's on the right side above my shift and enter buttons and below the backspace on my keyboard. So then I would do control. Well, is it control or?
It would be shift. Yes.
Yeah, shift.
Backslash.
Yes.
Okay.
Yeah.
Great. Yeah. I never know. Back and forth. Okay.
Yeah, I know. Because for me, to submit a line of code, it would be control enter, but I think on a Mac, it's different.
Yeah.
Alt enter, maybe.
Yeah, it's command enter.
Okay.
And it's always like sometimes I convert, like I would switch over into PC to use SAS on my Mac. And I just get confused by it all. So
I know I switch back and forth constantly. And so then I'll be back in my SAS windowing environment. Thanks everybody for joining. We appreciate your thank yous in the chat. And then
I have one last question.
Oh, Yes,
Sure,
please
yeah.
go ahead,
I'm so
Caitlin.
sorry. I didn't want to interject, but
Oh,
I
Yeah.
had
no,
another
no, no, please
question.
do.
I had another question about tables. So tables are actually extremely difficult at times to create,
Mhm.
especially when you have a ton of different variables. So like one thing I've been really working on with continuous variables and splitting that just based off of like demographic data, or other continuous variables that you turn into a categorical variable. Anyways, is there a really good way using table one package to also include um, like I guess missing data with also percentages as well as like the counts itself,
Yeah. So
just
generally,
with continuous data.
yeah. So generally, this is actually is going. So table one will actually create a missing level for you. So for continuous data. So let me show you an example. So like if we take the cars data set, and then let's say let's just look at like something random. So like let's say I'm gonna do something where I take horsepower and I'm going to I'm going to change this variable such that um, any value that's like, let's say less than 150 um, is NA. So, okay. So yeah, what I'm saying is that for this variable, and then I'm using these brackets to say, in the event that it's less than 150, I'm going to assign this to NA. Or let's see, what did I do wrong? I had the arrow going the wrong way. There we go. Okay, so now if I open up the data set again, and I select down to horsepower, and I scroll to the bottom, there's now going to be a bunch of NAs where there weren't before. So now if I use the table one function, and let's say we want to look at horsepower, and let's say cylinder, and I don't know how it wants me to spell it. This is why sometimes I like SAS better than R because it doesn't matter if it's capitalized. All right. Um, so let's see here. Okay, yeah. So like, do you see how it created, and I guess there were more. This is revealing how little I know about
Yeah,
cars. So um, here, like our grouping variable was cylinders, and so now it's actually created, and what it's saying is that, which I guess makes sense. Again, I know basically nothing about cars, but now like fewer cylinders has lower horsepower, and so now a bunch of those have like there's a dedicated missing category. Is that kind of
got
what you
it.
were talking about?
Yes, that's perfect. Awesome.
Yeah.
Thank you so much. This is
Mhm.
really helpful.
Yeah, of course.
Have a good night, guys.
Yeah, you too. All right, I think I'm gonna stop recording.
Great.
All
Joey,
right.
do you have any final questions before we end seminar?